All right. Hello, everyone. Let's see here. So last time we were reading this paper called Down with Determinants by Axler. Let me pull it up again real quick. And we made it to a section where I guess Cramer's rule was mentioned / maligned a little bit. So we were, I think, on this paragraph. I find it hard to conceive of a situation in which the numerical value of the determinant is needed. Cramer's rule, because of its inefficiency, is completely impractical, while the magnitude of the determinant is an indication of neither the condition of the matrix nor the accuracy of the solution. Now, here's the thing. I agree with this statement. Like, you would not use Cramer's rule to kind of numerically, to do numerical computations, but I hesitate. I feel like this is kind of a red herring because Cramer's rule is very useful in other ways. I mean, there are reasons why it's worth learning. So I wanted to just briefly describe what Cramer's rule is and do something cool with it. So I have an animation actually that I've prepared. It'll probably pop up once you guys know what Cramer's rule is. So let's just talk really quickly about what Cramer's rule is. So the idea of this rule is that you have let's say, a system of linear equations, okay? So you have a system of linear equations, and you want to come up with a formula for the solution. So let me write the system of linear equations kind of abstractly. So let's do a 2x2 system. So you have ax1 plus bx2, and then the other line is maybe cx1 plus dx2. And we'll say that these are equal to, let's say, y1 and y2. So this is a completely kind of arbitrary and abstract setup where I'm looking at a system of two equations and two unknowns. By the way, if you know a little bit, you know that whenever you have a system of linear equations, you know that there are only three possibilities for that system of linear equations. And those three possibilities are either there's a unique solution, there's no solution, or there are infinitely many solutions. And so Cramer's rule is only really helpful in situations where there's a unique solution. So you need to have as many equations as there are unknowns in order to use Cramer's rule. So you notice here there are two unknowns. In this situation, the unknowns are x1 and x2. And there are also two equations, right? So these two, I know I wrote G instead of Q, but there are two equations. There's this one and this one. So, you're in a situation where there are two equations and there are two unknowns. And so, Cramer's rule has a shot over here. And so remember, the promise is that if you use this rule, you can write a formula for what x1 and x2 is. Of course, there are faster ways to solve for x1 and x2 if you have row reduction, but this one will actually give you a formula. So how do you do this? Well, first of all, the first step is to rewrite this as a matrix equation. Okay, so just rewrite this as an equation of matrices. And so basically what this is saying is that the matrix A, B, C, D times the mystery values x1 and x2, these are the ones we do not know, should equal y1 and y2. Okay, so the matrix ABCD times the mystery values x1, x2, these are the ones we don't know, should equal y1, y2. So keep in mind, ABCD, y1, y2 are all knowns here. x1, x2 are the unknowns in this situation. Okay, here's what I'm going to do. In order to solve for x1, I'm going to kind of add stuff to this matrix equation, okay? So the matrix equation currently says ABCD times x1, x2 equals y1, y2. So let me add something to this. I'm going to rewrite this. ABCD, x1, x2, 0, 1. So I threw a 0, 1. Okay. Equals, well, what'll this equal? Well, I added an additional column to this second matrix, the one that I'm multiplying by. So to this x1, x2, I added the column 0, 1. Okay. And so what's going to happen here is I'm going to get y1, y2, and this is going to get an additional column as well. And the additional column that this is going to get is the column that happens when I multiply a, b, c, d by 0, 1. If you're reasonably familiar with matrix multiplication, hopefully this makes some sense to you. So if you multiply a, b, c, d with 0, 1, you should get b, d. All right? Hopefully, so far so good. Also, let me move this. Makes sense. Let's see here. Let's erase the start and just put this second equation up top. Okay, so hopefully the steps I've made so far are making sense. You know, all I did was add an additional column to this system. So hopefully not too complicated. By the way, I could also have added an additional column like so. Let me hold on. I need to unselect, deselect. Okay. I can also add an additional column to the system as follows. So instead of adding a second column of 0, 1, I can also add a first column of 1, 0. So let's try that. So I can do it like this too. A, B, C, D, 1, 0, x1, x2. Now this should equal A, C, y1, y2. Hopefully this so far makes perfect sense, but please let me know if it does not make sense. So, you know, you have these two things. Now, remember what I mentioned last time. Determinants are multiplicative. So the determinant of a product of two matrices is the product of the determinants of the two matrices. Now, let's see what that means here. So if I use the fact that the determinant is the product of the product is the product of the two determinants, well, first and foremost, what is the determinant of this first matrix over here? The determinant of this first matrix is just AD minus BC. Right? So the determinant of this first matrix is AD minus BC, right? Let's look at this first system over here. So once again, I'm using the fact that the determinant of the product in this situation is the product of the determinants. So this one, if I take determinants on both sides, this becomes AD minus BC. Agreed? Okay. What happens if I take determinants of this second matrix over here? If I take the determinant of the second matrix over here, it's going to become x1 times 1 minus x2 times 0, which is just x1. Right? If I take a determinant of this second matrix over here, it's going to be y1 times d minus y2 times b. So this is y1d minus y2 times b. So remember, all I did to this first system is I just took determinants on both sides. But notice this is giving me a formula for x1 because it is telling me that x1 is precisely y1d minus y2b over ad minus bc. How about that? So this is in essence Cramer's rule. Of course, I've only done it for 2 by 2 matrices, but I'll describe what happens. I'm sorry, Jennifer Buckley says x2. Did I mess up? Well, I think I only did the first one. Okay, maybe I said it wrong, but I think everything I've put on the screen so far is correct. Oh. Thank you, Helga Bjorn. I hope I'm saying that correctly. So in any case, there it is. So x1 is y1d minus y2b over ad minus bc. Lovely. And you can do the same thing with the second one too. It's pretty simple. So once again, we're relying on the fact, and we talked about this last time, we gave kind of an abstract proof of this last time, that the determinant of the product is the product of the determinants. And basically it's the same situation here. For the second equation, we'll get that x2 is equal to y2a minus y1c over ad minus bc. Lovely. Oh, I see. Yeah, yes. So in any case, this is what x2 is. This is what x1 is. Now, in general, the idea is exactly the same. You know, we just... If you have an arbitrary system of equations, so let's say you have a nice big system with the same amount of equations as unknowns. Okay, so we will collect all the coefficients of the equations in a matrix A, right? And the idea is that you're multiplying A by a, just like a vector of unknowns, x1 through, let's say, xn. So A is, again, an n by n matrix, and you're multiplying this n by n matrix by a vector of unknowns. Okay. And this is supposed to equal y1 through yn. Now, the derivation of Cramer's rule relies on just padding this second vector here, the one that you're multiplying with. So you write A again. So A is still this n by n matrix of coefficients, right? And instead of writing x1 through xn, think about which one you're solving for. So let's say you're solving for the ith unknown, okay? So what you'll do is you will leave x1 through xn in the ith column of this matrix. And for the rest of it, you just put in the identity matrix. So it's just going to be 1, 0, 0, whatever, 0, 1, 0, whatever. You just keep going. And this will end in a 0, 0, 0, 1. So remember, you're leaving the ith column as x1 through xn. So this is the ith column over here. And notice when you multiply A by this, you ought to get, hold on, let me move my face because I'm about to cover exactly what I'm about to show you, the main point of all this. So, all right. So now, if you multiply A by this matrix, I mean, what do you ought to get, you know? So first of all, you're multiplying A by the first column of the identity matrix. So you should just get the first column of A. So let's say A were like V1 through Vn. Let's say V1 through Vn were the columns of A. If V1 through Vn are the columns of A, you multiply A by the first column of the identity matrix, you should just get V1 again, right? And then you get V2. In fact, the only thing that's swapped out is when you multiply A with x1 through xn, which should be y1 through yn. So this is the ith column here. It's y1 through yn. And then the rest are the same, so going all the way to the nth column. Okay. When you write down Cramer's rule, there's just kind of like a special way to write this down. You just write A, I, y. So this one here it's the same as A, except we are replacing the ith column of A with y, okay? It's the same as A, but we are replacing the ith column of A with y, okay? Perfect. And so let's do the determinant thing again. So if we do the determinant thing again, once again, I've run out of room, but that's not a big deal. You'll get that the determinant of A times the determinant of this matrix over here. Now, what's the determinant of this matrix over here? Notice it's the identity matrix everywhere except for the ith column. And in the ith column, the entry is xi. So this is just going to be xi equals the determinant of the matrix you get if you replace the ith column of A with y. Okay, so xi is just the determinant of A-I-Y. So the matrix you get if you replace the ith column of A with y divided by the determinant of A. How nice is that? So you get this direct, simple, clean formula for just the ith unknown. So this allows you to solve for the unknowns individually. Now, I want to say that there's another advantage of this formula, because you can kind of see how the formula for the unknowns changes as you change parts of A and Y. So what am I talking about here? Let me elaborate a little bit. We now have a formula for the ith solution, the solution to the ith unknown in a system of equations. However, one thing I want you to remember is that the determinant is a continuous function. Okay, I'm going to write this in big letters at the top, just so you always remember it. It's a very interesting fact. So the determinant is a continuous function. This fact alone is very, very, very interesting and also quite powerful. So let's see how your guys' intuition aligns with this idea. So the determinant is a continuous function basically amounts to the fact that, hello, Brian. So the determinant being a continuous function essentially amounts to the fact that if you slightly modify a matrix, so let's say you have some matrix A, okay? And remember, the determinant is a map that takes the matrix A to just a real number, right? So now if you fiddle around with A, if you just like mess around with A just a little bit, let's say you change one of the entries by like a tiny amount, that should also change the determinant by a tiny amount. This is essentially what I'm saying. So we covered like a ton of different formulas for the determinant last time, right? We covered a ton of different formulas for the determinant last time. And in all of those formulas, it was clear that the determinant was a polynomial function in the entries of the matrix. You could see this particularly in the kind of permutation definition of determinants that we talked about last time, where you run through the rows multiplying various entries. And if you do that, you see that the determinant is just essentially a polynomial. Like you can think of it as like a multivariate polynomial in the entries of A. And because it's a multivariate polynomial in the entries of A, that makes the determinant a continuous function. So if you're not changing A much, you should not be changing the determinant much. Okay? So let me do a quick intuition test. We'll see if and how anyone feels about this. Let's say in a computer, I randomly create a matrix. Okay, let's say I randomly create a n by n matrix. Okay, I just use the fancy pants random number generator in my computer, and I construct a matrix. If you do this randomly, what do you guys think? Do you expect the determinant to be? I'm sorry. Do you expect this matrix to be invertible or not? If you don't know about invertibility, let me rephrase it. If you pick n vectors in Rn randomly, would you expect them to be independent or not? Like if you just use your computer's random number generator, what do you guys think? Let's see. He did. Probably not, says Brian. Okay. Let me put it to you this way. We know that functions are invertible. We know that determinants, we know that matrices are invertible if their determinant is, I don't know what independent means either, probably invertible. I feel like it's harder. You don't know what independent means either. So let me just give you a quick overview, Jamie. So for example, 3 vectors in R3 are not independent if they don't all lie on the same plane, for example. Okay? So if you have 3 vectors that in R3 that are all contained inside a plane, then those vectors are not independent because you can express one of them as a linear combination of the other 2, right? Another way to think about it is 3 vectors are going to be independent if the parallel piped that's made by them actually has a volume. If you get a flat box, then they're not independent. And you can use this to check if matrices are invertible as well, though it does take a little bit of work. Okay, so the idea is, for example, if you like, you can even work inside R2. So two vectors in R2 are independent if they actually make a parallelogram that has some area. But two vectors in R2 are not going to be independent if they lie on the same line, for example, because then you get a flat parallelogram that has no area whatsoever. So I hope that answers your question, Jamie. So can't commute has guessed that this matrix will probably be invertible. And let's see. I feel it's harder to produce that randomly, at least one dependent vector. No, can't commute is correct. So let me show you this way. So the only way for this matrix to not be invertible is if it maps to something of volume 0, right? It maps to something of volume 0 if and only if the determinant is essentially 0. Well, not essentially, if the determinant is 0. So the idea is that you can get an invertible matrix if the determinant is any number other than 0, and you get a non-invertible matrix if the determinant is 0, right? So it's actually far more likely, and this is like intuitive reasoning as well. Well, this is intuitive reasoning, not entirely rigorous thinking, though it can be made precise. You get that basically determinants show you that most matrices, randomly chosen matrices, are going to be invertible. Okay, so just another. I assume my bias, my pro-determinant bias, is extremely clear at this point. But hopefully it's clear that most matrices, quote unquote, most matrices randomly chosen are going to be invertible. Let me ask you guys another question. And this is another really interesting thing that you can do with determinants, right? Let's say you take a matrix, right, that is invertible, or if you prefer, whose columns are independent, or if you prefer, a matrix whose columns make a parallel pipette that has an actual volume. Let's say you wiggle around a little bit. Actually, no. You need to know a little bit about open and closed sets to do what I'm about to do. But let me ask you another question. Let's say I take a matrix A that is not invertible. Okay. So let's say you take a matrix A, n by n, and let's say this matrix is not invertible. Okay, let's say it's not invertible. Can you wiggle some of the entries to make it invertible? So the idea is, can you change at least one of the entries a little bit to make this matrix invertible? What does your intuition tell you? So once again, to repeat the question, I start with a matrix that's not invertible, right? And I'm allowed to maybe change one of the entries, just a little bit, just a tad, just let's like nudge one of the entries a little bit. If I have a freedom to do that, can I make this non-invertible matrix invertible? What does your intuition say about this? Depends on how many vectors are linearly dependent. I feel like if you modify some entries, you can make all independent vectors. Okay. So using the power of also I didn't mean to like be unclear. I didn't mean to say you can only modify a single entry. I just mean in general, if you can wiggle around the entries a little bit, like all of the entries a little bit, you have the freedom to do that. Is it possible to make this matrix invertible? Now, yes, you're right, Jamie. But once again, remember I'm asking about an n by n matrix. So this is a matrix that exists in Rn. So it's actually very easy to prove this using the power, the immense and all-encompassing power given to you by determinants. It's actually very simple. So let's say you take your matrix A that's not invertible. Okay. Then take your matrix, another random matrix B that is invertible. Okay. What you can do is you can draw a line segment between A and B. Of course, this line segment is in R n by n, right? So, but you know how to draw the line segment between 2 points. You just do t times A plus 1 minus t times B and run t from 0 to 1. So the idea is that, you change each entry of A, you pin it to each entry of B, and then you draw the line segment between those two entries, and you slowly modify from A to B. Remember, t goes from 0 to 1. Let me know if this idea of making a line segment between two matrices in Rn squared is clear. If that doesn't make sense, just think about making a line segment between each of the entries of A and each of the entries of B. Okay? So here's the thing. We know that the determinant of A is 0. We know the determinant of B is not 0. So if you travel on a line segment from A to B, you know that the determinant over that line segment, so like, maybe A is here, maybe B is here. You travel on the line segment from A to B. You know the determinant here is 0. You know the determinant here is not 0. Because determinant is a continuous function, somewhere on the line, the determinant has to stop being 0. And this has to do with the continuity of the determinant. Okay? So you can get a lot of mileage out of the fact that the determinant, well, you can get a lot of mileage about knowing about determinants, right? So the idea is that you can go from a determinant equal to 0 to a determinant not equal to 0 on a line. So it's that you can actually use this to prove that matrices that are invertible are dense. This is another concept we haven't, you have to like go to a topology class to see dense. But you can actually use the exact argument that I've laid out over here to prove that invertible matrix, any matrix you pick is arbitrarily close to an invertible matrix. Okay? And once again, I want to, the reason I'm showing you guys this, well, it is very interesting, but the reason I'm showing you guys this is I wanted to kind of elucidate the powers that determinants give you, like how much determinants really add to your intuition at the end of the day, because you can make quick arguments like this. Dense in the reals? No, dense in the space of matrices. So like if you have an n by n matrix, you can just think of it as a vector in Rn squared, right? You can just think of it, any matrix, any n by n matrix is just a list of n squared numbers, right? So you can just think of it as a vector sitting in Rn squared. Right? So any n by n matrix, so for example, any 2 by 2 matrix is just a list of 4 numbers. You can think of it as a vector in R4, right? And so what I'm saying is among the quote-unquote vectors of R4, once thought of as matrices, the invertible matrices are dense. So every matrix is arbitrarily close to an invertible one. Okay? You can just wiggle around the entries of and a non-invertible matrix in the right way. And if you do it in the right way, you will get you'll get something that is invertible. Okay, Brian, I hope that answers your question. There's also something really interesting you can do with determinants, which became the thumbnail of this video. And this is called Lagrange interpolation. This is a very interesting thing that you can do, and don't worry. I made like a really neat animation of this. It's just coming up in a second, but I just want to tell you quickly what Lagrange interpolation is. Lagrange interpolation is very simple. So let's say you have like maybe 4 points in. You have 4 points inside a R2, right? If you like, you can say that they're 4 data points, whatever, right? You know that there should be a, let's see, if it's 4 points. So for 2 points, there's always a line that goes through them, right? For 3 points, there's always a quadratic that goes through them, right? So for 4 points, there's always going to be a precise cubic that goes through them. So I'm not really sure what it's going to look like, but there will be some, let's see. I don't really know what it's going to look like. Maybe something like this. There'll be a cubic that goes through these 4 points. Hold on. Ken Commute says, in the extreme cases when they're all parallel, you can change one entry of each. Would be how I would prove it. Well, can't commute. You can, though. I don't know. I would hope you use determinants because I just gave a proof that uses determinants. So it's not. Well, like I feel like any other proof is a lot of work. I think that drawing a line segment between a not invertible and an invertible matrix, and just showing that, and using the fact that the determinant is a continuous function, is like a one-line proof. There are other proofs, of course. I don't mean to imply that you can't prove it anyway that you like. So, anyways, Lagrange interpolation is the idea is just asking the question. Okay, that's cool. What is the formula of this polynomial, right? So if I give you n points in the plane, I can ask the question. What is the formula for the polynomial? Of the degree n-1 polynomial, the unique degree n-1 polynomial that passes through all of those points. Okay, how do we know one exists? So let's think this through for a second. All right. Let's say my points are, let's say I only had 3 points, okay? x1, y1, x2, y2, x3, y3. Okay, so you got some 3 points in the plane, let's say, and I'm attempting to solve for the unique quadratic that happens to go through these 3 points. Okay, let's think about how I might do that. By the way, if you're used to regression, this is not regression, right? We're solving for a single polynomial that precisely passes through the 3 points. So these polynomials are susceptible to much violent behavior, okay? Whereas like they're very susceptible to noise. If you're watching this video from a statistics background, we're not doing regression right now. We are solving for the polynomial that precisely, like for n points, we're trying to find the degree n-1 polynomial that precisely passes through those points. Okay? Now, how are we going to do this? So what is the equation of a quadratic? Well, the equation of a quadratic is, y equals ax squared plus bx plus c. Agreed? So in essence, I'm just solving for a, b, and c. Now, if the quadratic is to pass through these 3 points, that really just means that y1 has to equal ax1 squared plus bx1 plus c, and y2 simply has to equal a x2 squared plus b x2 plus c, and y3 simply has to equal a x3 squared plus b x3 plus c. Okay, and I'm sure if you've been paying attention, you see it. There's a linear system of equations hidden inside here. Let's write it out real quick. So the linear system of equations is, I'll write it in matrix form. So you go write it like this. 1 x1 x1 squared, 1 x2 x2 squared, 1 x3 x3 squared times, let's do CBA, should equal y1, y2, y3. Okay. So there's a unique quadratic going through 3 points if and only if this, does it have to be a quadratic? There's probably a cubic that goes through these points. Absolutely, but not a unique cubic. There are actually infinitely many cubics that go through these 3 points. I'm trying to show you that there's a unique quadratic that goes through these points. Like, there is a quadratic and it does exist. Hopefully that makes sense, Jamie. Okay, so yeah, if as I pump my degree higher, I basically get way more polynomials that can pass those points. But what I'm asserting to you right now is that there's only one cubic. I'm sorry, there's only one quadratic that goes through these points. And okay, how do you know? So essentially, I'm asking the question like, how do you know it exists, and how do you know that there's only one? Okay, so basically, one will exist if and only if this system of equations has a unique solution, right? So such a quadratic will exist essentially if and only if, a unique quadratic will exist if and only if this matrix happens to be invertible, okay? So a system of 3 equations in 3 unknowns, right? So essentially, if this matrix is invertible, I can call this, or let me put it to you this way. Since we did Cramer's rule, right? Essentially, I know, let's call this matrix A over here, right? And I hope you're around for the Cramer's rule section of this talk. It was right at the start, right? So if you're around for the Cramer's rule section of this talk, then you know that C is going to be precisely the determinant of A1 y, where this whole thing is y, right? This whole column vector is y, divided by the determinant of A, right? And B ought to equal the determinant of A2y divided by the determinant of A. And A should equal the determinant of A3y divided by the determinant of A. All right. Hopefully that, hopefully if you're around for the Cramer's rule part of this talk, these are just the formulas for the solution to this system of equations. Let me just move this over here. Just a little bit, so I'm not blocking it. Okay, I don't know where to move it. Okay, done. Deselect. Let me erase this A a little bit. Okay, so yes, drive safe, Brian. As I pointed out earlier, you actually have formulas for the solutions for A, B, and C, right? And so what you realize is that A, B, and C will always exist as long as the determinant of A is not 0. That's precisely what Can't Commute said in the comments, right? So A, B, and C will exist precisely when the determinant of A is not 0. And in fact, these are unique. A has to equal this, B has to equal this, C has to equal this. Okay? So Cramer's rule gives you an immediate quick proof that there's a unique quadratic that passes through these 3 points as long as the determinant of this matrix A is not equal to 0. And by the way, this proof generalizes to an nth degree polynomial. If I have if I have n plus 1 points sitting in the plane, right? What this is telling me is that there can be only 1 degree n polynomial that passes through all of those points. right? But there's a little bit of something I'm kind of leaving on the table here, which is I said as long as the determinant of A is not equal to 0. So when is the determinant of A not equal to 0? When is this determinant not equal to 0? What do you guys think? When is this determinant? When could it possibly equal 0, and when could it possibly not equal 0? Because remember, there's a unique quadratic through 3 points if and only if this determinant is not equal to 0. So essentially, it all boils down to us figuring out when this determinant is not equal to 0. And it turns out this determinant has actually a famous name. So this would be the so I'll name it. This is called a Vandermonde determinant. The determinant of this matrix is called a Vandermonde determinant. Okay. So the determinant of this matrix is called the Vandermonde determinant. Okay. And essentially, the claim is it always exists. Okay. So Trent Tobler says if y1 equals y2. So I'm assuming that you're trying to say that if y1 is equal to y2, for example, there won't be a unique quadratic. I hope I'm not putting words in your mouth, but that's actually not true. So y1 can equal y2, and there'll still be a unique quadratic that goes through them. The pain happens when x1 is equal to x2. Okay? So we're going to examine the Vandermonde determinant. And what I'm going to show to you is that as long as x1, x2, and x3 are all different, this will be an invertible matrix. In other words, its determinant is not going to equal 0. Okay? So as long as x1, x2, and x3 are different from each other, we should be able to find a unique quadratic or cubic or like whatever. Like I said, these arguments work in any degree you want to do them in. Okay? So I hope that makes sense. So I hope my claim makes sense. So the claim is that as long as all of these values are different, the determinant of this matrix is going to not be 0, which by Cramer's rule tells us there's going to be a unique solution. Okay? So how do we know that? Well, just so you know, the Vandermonde determinant applies for n points. So for example, if you had n points, the Vandermonde determinant would be the determinant of this matrix. It would be like 1 all the way down, then x1, x2, all the way to xn, then, x1 squared, x2 squared, all the way to xn squared, blah, 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 x1 to the n minus 1, x n to the n minus 1, whatever the determinant of this matrix is. Yes. Sorry about that. I see you meant x, not y. You're absolutely correct. Okay. So, by the way, the Vandermonde determinant in general for n numbers is going to be the determinant of this matrix. Of course, I'm covering myself up as usual. So let me just put this up there. Okay. Now I want to point something out to you. When we computed determinants, we gave a number of definitions for determinants, right? But in essence, this is going to be a polynomial, right? Notice that if x1 equals x2, or x2 equals x3, or x1 equals x3, we would get a matrix whose 2 rows are the same, right? Because the 2 rows would be the same, the determinant would definitely be 0. So it is definitely the case that if x1 were to equal x2, or x2 were to equal x3, or x1 were to equal x3, then 2 of the rows of this Vandermonde matrix would be the same. Also, I'm still covering myself. Hold on. Okay, I think that is a good position for me. Okay, so for sure, if x1 were to equal x2 or x2 were equal to x3, or and so on, then then for sure the determinant of this matrix will be 0. And also that's it, because you can think of this as a polynomial, right? The Vandermonde matrix, right, will always, if you just multiply it out, if you just think of x1, x2, and x3 as just variables, this is a homogeneous polynomial, and the degree of this polynomial will be n times n minus 1 over 2. Okay? So if you just think of x1 and x2 and x3 as variables, then this is a polynomial, all of whose terms have the same degree, and the degree of every term is n times n minus 1 over 2. Okay? And we know that it has factors. So by the way, in this case, you can check it. So for example, if you compute this determinant out, it would be like x2. So for example, one of the terms would be x2, x3 squared, right? And then minus x3, x2 squared, and so on. You know, there'd be 6 terms in total for this polynomial. But notice the degree of each term is precisely 3, right? Which is, hopefully that makes sense. Okay. Also, you know that x1, like xi minus xj is always a factor of this polynomial. So you know that x1 minus x2 must be a factor of this polynomial, x2 minus x3 will be a factor of this polynomial, and x1 minus x3 is going to be a factor of this polynomial. So because each term has degree 3, we found all the factors, essentially. So the only way that this determinant can be 0 is if 2 of the x values are the same. Okay, so you know, think about it for a second. It's not too bad. So this is just a polynomial. Think about what its degree is, and then think about the fact that you know all the factors of this polynomial, and so those factors have to be it. Essentially, the factors will be x1 minus x2, x2 minus x3, x3 minus x1. Okay, all right. Can't Commute says it makes sense, which is good. Now the neat thing about having we proved the theorem using the Vandermonde determinant and Cramer's rule. We were able to prove that if you have n plus 1 points in the plane, and you know no 2 points have x values on top of each other, right? There should be a unique polynomial that goes through those points. Okay. Now, I actually prepared something for you guys. Let me just open it up. So I did this in Mathematica last night. Let's see here. So let's start with a fancy function. So this is just a circle. So I'll use the second function, which is like a little bit fancier. So this is a plot of the function. Let me zoom in. This is like a complicated parametric function, and oh, it's too big. You can't even see it. Hold up. Oh God, what am I doing? Okay, so this is the function we're dealing with, and the only reason I have this function is that I would like to plot like a bunch of points traveling around this function. Okay. So what I'm going to do is I'm going to take 7 points, and I'm just going to have them. Let's see here. Hold on, I'm like giving away the like reveal. What is okay? So you can have 7 points kind of just like traveling around this function, and it's really neat because those 7 points always travel in an ellipse, which is really cool. So let me like have them travel slowly. So let me play forward, just slow it down. Okay. Hopefully, like my stream can handle this this amazingness. But I think this is really neat. So you know, you have these 7 points. They're traveling around, and they're always in an ellipse. Okay, which is kind of interesting to think about. So this is all just like basic setup, right? Here's the thing. I should be able to come up with polynomials that basically go through these points, right? Because they're just a bunch of points in the plane. So there should be a unique 6th degree polynomial that goes through all of these points, okay? And what's even more interesting is, because of our formulas and because we know determinants are continuous, as these points move, the polynomial should also smoothly move, okay? So as these points change, the polynomial should also change smoothly. Okay, so I hope you're excited about this. So what I'm going to do, just so like the graph isn't too busy, I'm going to delete the like path that they're moving around so that you just see the points. Okay, so let's get rid of this. And just show the points, I guess. Darn, it like rescaled the graph. Let me just see, graphics red. Just need to do a black background. This is just me having fun, by the way, if that wasn't completely clear. So, what? Oh, I have 2 commas. Okay, so I got rid of the like path, and hold on, I need to slow it down. Okay, so I got rid of the path, and these are now the 7 points, just moving around. Okay. Hopefully, I don't know how it's going to look like on stream, but hopefully the smooth motion of these points, just beautifully waiting around, is abundantly clear. Okay. Now what we can do is we can solve for the Lagrange interpolating polynomial that goes through all 7 of these points. I hope you guys are very, very excited about this. So what I can do is here. Let me unleash the polynomial on it. Plots tell white. Hold up. Need to set up a black background for this one and no axes. Hold on, it's not showing up. Let's see, plot. Why is it unhappy with me? Let's see, so plot. Let me just erase these options potentially. Okay, that's weird. I guess I'll show it with the path. I didn't want to show it with the path, but okay. So yeah, I wanted to delete the like blue like path that the points are moving along at the end. Actually, I have an idea. Why don't I plot just like 100 and set my plot range here. Okay, perfect. I can show it with the path as well, if you like. But to play, slow down. Okay, and so now you should be able to see that the Lagrange polynomial that goes through these points changes smoothly as you move these points around. How about that? You can actually do a lot of fun art with this if you really want to. I really like making pictures with this kind of stuff. So but there it is. You just watch the 6-degree polynomial. And it does really cool stuff when like it has to shift over. And you can actually think of this as a complex polynomial. So there's actually like a going through infinity argument you can make as it goes like up and around. Okay. But in any case, there it is. This is a polynomial, goes through like a 6-degree polynomial going through 7 points. And by the way, I have the code set up so you can just like change the number of points. So I don't know. I'm just kind of curious what happens if we change it to 10 points. What strange violence will happen. So let's see. Hit play here. Ooh, that's interesting. Here, make it go a little slower. This is now a 10th degree polynomial going through I'm sorry, a ninth degree polynomial going through 10 points, and you can watch it just kind of floating around. Okay, I just need it a little faster. So yeah, as you can see, I would clip this if this was Twitch. Oh, well, it ain't Twitch, but it is what it is. I don't know. I think this is really cool. And let me know if you guys like care at all. I can, I don't know. I can make like a GitHub page for this channel, and you can mess around with the code. I don't know how many people have Mathematica. It's just so easy to write this kind of thing in Mathematica. But yeah, like in Mathematica, I love watching when the points like go over each other. It's so cool. But yeah, in Mathematica, that was it. That's all the code I had to write to do this. I mean, come on, that's pretty tight. I like that a lot. So in any case, there it is. I guess like I wouldn't be doing my job if I didn't do like an absurd number of points. So let's do like 15 points and see what happens. Look at it go. Yeah, that polynomial is hitting every single point. Out of curiosity, what are your guys' like programming languages? Like, what do you guys usually use? Let me know. Yeah, this is giving me like errors because it's happening too often that like the point, like the points are on top of each other. So yeah, so that's like for a brief moment, it gives me a divide by zero error. Okay, you use JavaScript. You know what? It would be very quick to do this in JavaScript as well. Well, actually, I take that back. It would be very pretty to do this in JavaScript because, there's just like a lot of cool, like, well, you just hit something, you just view it in the browser, and you can show lots of cool animations in the browser. I think you'll start hitting numerical instability at this level. Oh, for sure. Well, it's not too bad. I think the only issue is that sometimes these points, they like travel over each other, and then you get a divide by zero error. Lagrange polynomials are inherently unstable. There's actually a great picture on Wikipedia. I'll show you right now. So you see this? Okay. So this is just a Lagrange interpolating polynomial approximating a bell curve. Okay. So here, let me zoom into this picture. So it's supposed to be approximating this bell curve, but you see the approximation is kind of wild. Like it looks pretty good at the points at the top, but it does not look very good. Like it's not a good approximation for the points on the side. So I would not recommend using Lagrange interpolating polynomials for your approximation needs. Though they're a lot of fun to use for your like artistic needs. There's like a bunch of analysis arguments where they come in super handy because it's just nice to know that there's this like lovely, smooth, like continuously changing polynomial that'll pass through all of your points. Okay. I would not. Well, maybe we can go over regression at some point because it's pretty interesting. But for now, yeah. Just for now, I just wanted to convey to you that. You can do lots of interesting and cool things with determinants. So anyways, that's that. Let's see. Let's maybe... Oh, one other thing I want to mention is, so the formula that I gave you for this polynomial is going to be, the coefficient of like t to the I will be something like, the determinant of a I minus 1y over the determinant of a. This is a lovely formula, but it has been broken down even further. So if you want to look it up, or if you like, I can talk about it too. Let me know if you guys are more interested. The formula has been broken down further to give like a slightly easier formula for the polynomial that'll pass through endpoints. And of course, it was Lagrange who did this simplification. I think Newton did one as well, and they both worked this out. So let me know if you want to see it. It's a little bit off topic, but yeah. So let's see. When need nth degree regression to make every connection stick, it fits the data. Yeah. So this is it'll always fit the data. It will. A machine learning or a statistics expert would say that it would overfit the data, right? It overfits the data. It's extremely susceptible. So there's just like a classic trade-off in machine learning and statistics. The better you fit the data, the more vulnerable you are to like noise in the data, right? This is why you need really good like validation and stuff like that when you do things. Okay, in any case, that was my TED Talk on Cramer's rule, all the cool stuff you can do with it. I hope you're convinced that it's tremendously interesting. Maybe I'll spend like 10 minutes reading Axler, just so we can continue on. Let me know if you guys like this style, like just so you know, like the goal of this is not to like just read the paper. It's to just like learn cool stuff along the way. But let's continue on. So eigenvalues and eigenvectors. Okay. The basic objects of study in linear algebra can be thought of as sets of linear transformations or matrices. Because a basis-free approach seems more natural, this paper will mostly use the language of linear transformations. Readers who prefer the language of matrices should have no trouble making the appropriate translation. Okay, there's a lot. Well, let me know how you guys feel about this sentence. How do you guys feel about this whole any linear transformation can be written as a matrix, and matrices are secretly linear transformations? I should say, in finite dimensions, this is true. But let me know if you've never seen this before. Though I'll keep reading in case it's not that important. So, the term linear operator will mean a linear transformation from a vector space to itself. Thus, a linear operator corresponds to a square matrix, assuming some choice of basis. Notation used throughout this paper: n denotes a positive integer, v denotes an n-dimensional complex vector space, t denotes a linear operator, and v, and I denotes the identity operator. I know every linear transformations. Haha, do you not like it? I'm not sure what you're saying, Brian. You'll have to clarify. Also, I just realized I never finished answering Bimal Pandey's question. So you can use JavaScript, and your animations will look way prettier than mine. Let me drop down the number of points. Let's try 11. All right, well, actually, let's go back to, let's do 6. So your animations will look way prettier than mine if you use JavaScript. The issue is stuff like writing easy invert matrix code. You'll have to like access a library to compute a determinant. Just doing math in JavaScript. Based on my memory, I was a web developer it's been 7 years now since I last did any web development code. But I am like somewhat familiar with JavaScript, and so the issue is just doing math in JavaScript is not fun. And I think Can't Commute said that they know Python. So doing math in Python is actually it's not as good as Mathematica, but they're you have NumPy, you have lots of great libraries to just do computations very well in Python. The issue is making animations easily. I don't know how easy it is to do that. I've looked into it slightly, and making animations in Python, it did not seem like a natural thing to me. Though I think the famous 3 blue 1 brown makes all his animations in Python. So maybe maybe we can figure it out. Personally, I'm very comfortable with Mathematica, it's so fast. I mean, all this took me like 30 minutes, and look at just like a couple lines of code, and look at that. And it's completely flexible. I can change the number of points, blah blah blah. All right. So all right, thank you, Brian. All right. So maybe next time we'll talk about this whole linear operator to matrix business, and then we can discuss the proof in Theorem 2.1. Every linear operator on a finite dimensional vector space has an eigenvalue. So there's two proofs you can give of this statement, of course. There's one that relies rather heavily on determinants, and there's one that doesn't rely at all on determinants, right? So, you know, maybe just to be balanced. Actually, no, like I said, I have an extremely pro-determinant bias, but I'll present both proofs. I'll present Axler's proof that, you know, it's, that doesn't require determinants, and I'll provide the standard proof, which does use determinants. All right, I think like the hour's up. Yeah, you have to learn the package that does the thing every time you do something. That's true, yeah. But like, Python's a lot faster than Mathematica, for example. If you know what you're doing, Python should be significantly faster than Mathematica. So I think I'll just leave it at that. I mean, it's been about an hour. It's pretty reasonable. Hopefully you enjoyed all the stuff that you learned today, and I hope you're inspired to do something artistic or interesting, you know, maybe with the Lagrange polynomials. That'd be really fun. If you want the code at all, just let me know. Just leave a comment in chat, and I don't know, I'll make like a GitHub page or something, and I can just upload this file, and you can mess around with it all you want. Maybe I'll leave a comment or two so you know what the heck I did. I'm very bad about leaving comments, especially in code that I write for myself. If there's like another person who's going to read it, I always am good about writing comments, but I'm not. If I'm just like hacking something together, I never put in comments. So yes, I'm a bad programmer. But other than that, I think that's it for me. So I'm gonna head out. Let me know whatever you want me to talk about. To be honest, I don't really care. If there's any mathematical topic you're interested in, I'm happy to dive into that. I can keep reading this determinant paper. It's pretty interesting, and I do love linear algebra. At some point, I do want to get back to reading sections of Hubbard, which was like the first stream I ever did. But other than that, I think that's it out of me today. So I'll see you guys again on Saturday at 1 p.m. And I think that's all I got to say. So see you guys, and peace.